Alright, so I'll take the king of clubs. What we're going to do is give it a little bit of a flick here, just like this. If you do it enough times, it'll change into the ace of hearts. What's up, everybody? Hope you're doing well. Back with our coffee, maybe? I don't know. And yeah, I got this after I got married. Anyways, I just want to give you a quick update on what the rest of the year is going to look like in terms of assessments. So, you guys get the email from Mr. Harris saying that we're not going to have a final exam. So, instead of having the final exam for Algebra 2, what the rest of the year is going to look like is you will have your test on Chapter 4, and that's going to be the last test. Now, I said you guys aren't going to have a binder check. I will be dropping the lowest 200 points, so that should take care of everything to make everything as fair as possible and accurate as possible. So that's what it's going to be for Algebra 2. Just one more test, you'll have one more quiz the last week of school before the 12th, and then that'll be it. Alright, for geometry, what you guys are going to be doing for your final assessment is you're going to take the study guide that you would have done beforehand to prepare for the test, and that's going to be your final. So today I'm going to post the final study guide, and you guys will have to get that done before the 12th, and that's going to be our entire scope of the semester. So that's the last assignment that you guys will have to do for the quarter. Now you guys do have a test on chapter 12 and 13, and that's going to be due the same day as the final exam study guide, but I'm going to kind of scale back the homework to make it a little bit easier, just so you guys can not get overwhelmed, hopefully. So yeah, that's going to be our, again, final exam is the final exam study guide. If you guys have any questions about that, make sure you let me know because it might be confusing. I hope not. Hope I explained it pretty well, but that's what we're going to be doing. I'll probably shoot out an email kind of explaining everything too. Alright, that's it for me. Enjoy the lectures. Alright, so today we're looking at 13.2, which is all about theoretical and experimental probability. So first, let's define what probability actually is. So probability is the measure of how likely an event is to occur. Each possible result of probability experiments or situations is called an outcome. The sample space is the set of all possible outcomes. These can be listed in a tree diagram, an organized list, or a table. So when we look at probability, we're just saying what's the likelihood of something happening. Now, for each result, we're going to say that's an outcome. So say I flip a coin, what are my possible outcomes? Well, I can get heads or tails. The sample space is all possible outcomes. Now, the sample space is all based on counting. So the permutations, combinations, fundamental accounting principle, that's a way that we can count all possible outcomes, the sample space. Now, once we get all possible outcomes, we can list these if we want to in a tree diagram, or just a list, or a table. So you can write out everything if we want to. Usually you don't have to, but sometimes it's helpful to kind of get a visual of what's going on. So let's say that we're going to flip a coin 3 times. Let's look at the total possible outcomes, or let's look at the sample space. So we're looking at the sample space. We need to count the total number of outcomes possible. So I flip a coin 3 times. if I'm going to flip a coin 3 times, let's go ahead and use the fundamental accounting principle to see the total number of outcomes. So there's my first flip, second flip, third flip. In my first flip, what are my 2 options? Well, I have heads or tails, that's 2 options. I flip the coin again, I get 2. Flip it again, I get 2. So I get 2 cubed, or 8 possible outcomes. So that would be an example of sample space. Now, if we know I'm using the fundamental accounting principle to get 8 possible outcomes, let's go ahead and list all the possible outcomes. So my first flip, and we're just going to go through every different scenario. So say my first flip I get heads, I can flip it again and get heads again. That's one option. I could get heads, heads, tails. I could get heads, tails, heads. I could get tails, heads, heads. I could get tails, tails, heads. Tails, heads, tails. Heads, tails, tails. And then lastly, tails, tails, tails. And that's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So this is the entire sample space. That's every different possible outcome. Now a tree diagram, and this would be our list. A tree diagram is where I start with my quarter, or your coin, whatever it is. Just say it's a quarter. Now I flip it. My first flip, I could get heads, or I could get tails. Now say I get heads, I could flip it again, and I could get heads or tails. So this is my first flip, second flip, third flip, heads or tails, heads or tails. Now let's say I got tails on my first flip, my second flip, get heads or I could get tails. My third flip, I could get heads or tails. I can get heads or tails. So you see that this is my 3 flips here, and we're just going through all the different routes or branches of the tree. And this is called a tree diagram because it kind of looks like a tree. So what are my options? Well, if I count all my final spots here, notice you get 8. Now let's use a table to show the sample space. So these last three examples were just looking at the sample space. How do I identify the sample space? Now question 2 here says you roll two 6-sided dice and we find the product. So the way we're going to do this for a table is I have my first die, 1 through 6. Second die, 1, 2, 3, 4, 5, 6. And I'm going to be finding the product. I'm going to multiply. So the way I do this, if I roll 2 1s, 1 times 1 is 1. Let's say I roll a 1 and a 2. It's going to give me 2. 1 times 3 is 3, 4, 5, 6. And I get the same thing down that way. 1, 2, 3, 4, 5, 6. Because I roll my 2 dice and I just multiply the outcome. Well, let's say I roll a 2 and a 2. Multiply those together, get 4. Roll a 2 and a 3, multiply them together, you get 6, 8, 10, and 12. Let's say I get a 3 and a 2. I can keep that same pattern, so I get 6, 8, 10, 12. 3 times 3, that gives me 9, 12, 15, 18. 4 times 3 is 12, 16, 20, 24. 5 times 3 is 15, 20, 25, 30. 6 times 3 is 18, 24, 30, and 36. So this would be my table if I'm multiplying my results together. So that's just the three different ways to write the sample space. Now once I get the sample space, I can use it to find the probability. So theoretical probability for equally likely outcomes, there's no weighted events occurring, we're going to say that P of the events, and we've talked about this before, but I'm going to say P of what I want to happen. So this right here is just what I'm looking for. Maybe I'm looking for a heads being flipped or rolling a 6. I'm going to say P of the events is equal to the number of favorable outcomes, or what I want, and divide that by the number of outcomes in the sample space, or the total. So want over total. That's what I want you guys to remember. But this is the actual way we can say it using the correct terms. Favorable outcomes over number of outcomes in the sample space. So we can say want over total. So let's say that we take 2 pennies, and I toss 2 pennies. What's the probability that one will be heads and one will be tails? Well, first let's calculate the sample space. Well, my sample space, if I flip both, I get heads heads, heads tails, tails heads, or tails tails. Or I could just do 2 times 2. My sample space is 4. I have 4 possible outcomes. That's my total. And I'm looking for 1 head and 1 tail. Well, when I look at these 4 options here, where do I see 1 head and 1 tail? Here's 1 head, 1 tail, 1 head, 1 tail. It doesn't say which order I want it to be in. I'm just looking for heads and tails. So the probability we get 1 head and 1 tail is going to be equal to 1, 2. That's what I want. And my total is total possible 4 outcomes. So I get 1/2. That's what this probability would give me. So I could say P of 1H, 1T equals 1/2. Or you could also do 0.5. That's okay. Do not use a percentage. Don't do that, because percentage is chance. If you use percentage, I'll dock you probably 0.5 point. So use a fraction or a decimal. And the other thing too with probability, if you're calculating multiple events, it falls in a range of 0 to 1. That's where your probability has to fall, where P of 0 means that it's not going to happen. It's 0, not going to happen. P of 1 means it's going to happen, and then let's say you get 0.1, that fall over here. That's going to be not as likely. If you got 3/4, that's more likely. But let's say you do something and you calculate the probability of an event occurring, and let's say that you get your probability is 7/5. Well, the issue here is that it's greater than 1. So you can't get a probability that's greater than 1. The max probability you can get is 1, because if you have a probability of 1, that means it's going to happen. That's the highest you can get. So that's just something to be aware of. If you get a number greater than 1 or less than 0, you probably did something wrong. All right, number 4, how many outcomes are there if a penny, a nickel, and dime, and a quarter are tossed? So show the sample space. Now, this sample space, you get a really big outcome here, and I'll show it to you guys. So this is the sample space, making a table of it. So quickly I'll explain it. We have our pennies, nickels, dimes, and quarters. I could get a penny on my first flip, heads, heads, heads.
I could also get the outcome of a heads, 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 tails for the quarter. Get heads, heads, tails for the dime, and the heads for the quarter. And you just do every single possible combination here, every ordering, or this combination is better, combination. So these are all the different outcomes here. So I suggest going and either pausing the video and copying it down or trying to figure out on your own. But this is basically the same thing when I had this one, heads, 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 tails, tails, heads, tails, tails. It's the same thing, just with 4 different coins. The same concept. And the question in example B, or question B, what's the probability that 2 heads will occur? Well, first let's find the sample space. So what's my total number of outcomes? Well, I could just count all these, like get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hold up, I missed one. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, good. So there's 16 if we count them all. Or, I know that for my first coin there's 2 options. 2 options for the nickel, 2 options heads or tails for the dime, and then quarter, 2 options. Using the fundamental accounting principle, I can multiply these all together. 2 to the 4th, which is 16. So both ways are fine. But in this example, it will be helpful to have the table, because we're looking at the probability that 2 heads will occur. So it will be helpful to see what we're working with. So we're going to say, I'm going to erase this for now, the probability that exactly 2 heads will occur is going to equal to what we want over the total. Well, we know the total. The total is 16, right? There's 16 possible outcomes. Now we want 2 heads. So in this table here, where do we see exactly only 2 heads occurring? Well, this one's out. No, 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 because there's 3 heads. Here we have exactly 2 heads. Exactly 2 heads right here. 2 heads, 2 heads, 2 heads. This one's out. This one's out, 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 and out. So in these here, which we have 1, 2, 3, 4, 5, 6, and those 6 outcomes, we have 2 heads occurring. I think I might have missed this one right there and right there. So we have 6 outcomes there. So we have 6 wanted outcomes, 16 total, which reduces to 3/8. So the probability that you'll get 2 heads if you take a penny, nickel, dime, and quarter and toss them will be 3/8, or 0.375. Now as a chance, if I convert to chance, that will be 37.5%. But again, if I don't ask for chance, don't put percentage. Probabilities in fractions or decimals. Now, as I was saying before, your probability has to be greater than or equal to 0, but it also has to be less than or equal to 1. So if you take all the probabilities in your sample space, and you take them, add them up, you take the sum, you're always going to add to 1. So what that means is, if I take probability, I flip a coin, I get heads or tails. Well, heads is going to be, probability to get heads is 1/2. The probability to get tails, That's 1/2. You notice if I add both together, it equals 1. So the sum is always going to be 1 in their sample space. Now next we're going to say the complement. The complement of an event is the set of all outcomes in the sample space that are not in the event. So what this means, we're going to say that the complements, let's say we have our event, there's going to be E with a C as the exponent. The complement, or we can say not E. So the probability of the complement of event E is going to be probability of not E. So not the event occurring. That'll be equal to the probability of, we can say EC, or we can say 1 minus the probability of that event occurring. So if I can calculate the actual event, I can do 1 minus that probability of the event occurring, and that will give me the probability that it will not occur. So sometimes this is really useful because if I want to calculate an event, I can calculate the way it won't happen and then 1 minus that to calculate the event. So it's kind of like a go-around little trick. So let's practice that. Let's say that example 5, battleships play with 5 ships on a 100-hole grid. At the start of the game, what is the probability that the first shot misses or missed all the other targets? So when I say misses, this is the same thing as a not hit. So if I'm going to use the complement, what I can do to calculate the probability of a not hit or a miss, that'll be equal to 1 minus the probability that you actually hit on your shot. Well, we have 5 ships, 100-hole grid. When we look at this table over here, we see that if you have 100 holes total, how many of those holes are being covered? Well, a destroyer takes 2, cruiser 3, submarine 3, battleship 4, carrier 5. If I add all those up, you get a total of 17. 17. So what we can do is say the probability of not hitting, that'll be equal to 1 minus the probability that you hit, which is 17 over 100. Well, I'm just going to do NH for not hit. That's going to be equal to 100 over 100, which is 1 minus 17 over 100. That will give me 83 over 100, and that's the probability of not hitting or missing on that shot. So with this one, obviously it would be easier just to, use a little bit of subtraction at the beginning and not do the complement, but this is just a way for me to show you guys and give you a quick example of how you can use the complement to solve a probability. And sometimes that is necessary to do. Alright, number 6, example A. If the 14 boys on the BCHS baseball team are each assigned a jersey number from 1 to 14 at random, how many possible jersey number boy arrangements are there? So for the total possible outcomes, let's say you have all the jerseys. 1, 2, 3, all the way up to the 14 jerseys. And you have all 14 boys, all the way up to 14. Now, let's see, the first boy comes, he picks a jersey. Well, how many, for the first jersey here, how many different options do you have? You have 14 total, and then he's taken. Next one, you have 13 boys remaining. Then you have 12 boys remaining, all the way down to 1. So this is your 14 factorial. So the total number of possible number boy arrangements are 14 factorial, which will give you 87 million. Oh, that's not million. Timeout. 87, 178, 2, 3, 1, 2, 3. So 87 billion, 178 million different arrangements, which is a ton. Now, if the jerseys are handed out at random, what's the probability that Matt's jersey will be number 1 and Jared's jersey will be number 2? Well, the way we can calculate this one is, let's assume, so we're looking for the probability that Matt is number 1, Jared is number 2. So what's that probability? A way that we can count those outcomes is, because when we do what we want over the total, let's say that Matt has to get number 1. Well, how many ways are there for Matt to get number 1? There's one. Only he can get it. Again, using the fundamental accounting principle. Jared needs number 2, so how many ways are there for Jared to get number 2? Well, 1. Because Jared needs that one. There's 14 boys total. Matt and Jared have gone, so how many boys are remaining? There's 12. Now, we don't really care about what numbers they get, but they still have to go in order, so they'll get 12 options for the next jersey, then 11, then 10, all the way down to 1. Or we can just write that as 12 factorial. So for the event of Matt and Jared getting their jerseys, the total number of outcomes of what we want, that's just going to be 1 times 1 for Matt and Jared times 12 factorial, or just 12 factorial. So the way that we can write this probability, we're going to set the probability of Matt, we'll just say M number 1, and then Jared number 2. That's going to be equal. So the probability that Matt gets number 1, Jared gets number 2 is going to be 12 factorial over the total, which is that 14 factorial, which will be 12 factorial over 14 times 13 times 12 factorial. Those cancel, and you're left with 1 over 14 times 13, which will give you 1 over 182. So that's the probability that Matt will get number 1 and Jared will get number 2. Number 7, Brielle has a choice of 20 flavors for her triple scoop cone. How many ways can she choose 3 different flavors at random? So for this one, we have to ask ourselves to count the total number of outcomes, the sample space. Do we care about the order in which she's picking the flavors? Well, no, the order doesn't matter because she's just making a grouping of 3 different flavors. So this would be a combination. So looking at a combination, we're going to have NCR. Well, the total number is 20. So 20C, how many is she selecting? 3, 20C3. So using our formula, we'll get 20 factorial over 3 factorial times 20 minus 3 factorial. That's going to give you 20 times 19 times 18 times 17 factorial over 3 times 2 times 1 times 17 factorial. Those cancel out. 3 times 2 is 6. 6 or 18 divided by 6 will be 3. So that will give you a total of 1,140 different outcomes. And that is your total sample space. Question B, what's the probability that she will choose vanilla, chocolate, and strawberry? So for vanilla, chocolate, and strawberry, how many ways, now this one you gotta be careful because we're not looking at a specific order, so it's not like the heads, then tails, and then tails, and heads. We're going to say she's just taking a grouping of those three different flavors. So when we're looking at just selecting three different flavors, not a specific order, how many ways can she get vanilla, chocolate, and strawberry? Well, there's only one way to have those three flavors if she's selecting a grouping. So the reason that it's 1 for what you want to occur is because you're taking these three flavors. If we were to look at, we're trying to make a grouping out of those three flavors. So this would be a combination, and you have three flavors that you want, and we're selecting three flavors. So it's 3, C3, which will give you 3 factorial over 3 factorial, and 3 minus 3 factorial. Well, it's going to give you 1 over 1 because the factorials cancel out. 3 minus 3 is 0 factorial, which is just 1. So you have 1 over that 1140. And that is the probability of choosing vanilla, chocolate, and strawberry. Now lastly, we're going to look at experimental probability. Now experimental probability is equal to the number of times a desired outcome occurs run out of space over the number of trials. So really the difference here is that with experimental probability, you actually have, you're running trials, you're running an experiment. Whereas theoretical, you're calculating the total number of possibilities. Whereas with experiment, you're going to be given, like I said, those trials. So the example here, the table on the left shows the results of spinning a spinner with numbers 1 through 4. What's the probability that you'll spin a 4 on the next spin? So here, we're actually given outcomes. Now, to do this, we're going to count the total number of trials that were ran. So notice that with a 1, I spun a 1 6 times, a 2 was 11, spun a 3 19 times, and a 4 spun 14 times. So if I add all these up, I get a total of 50. So I ran 50 trials. So that would be my total number of trials ran, or my sample space, basically. So I'm looking for the probability of spinning a 4. So what I want over the total, but in this case we have total trials. So probability of spinning 4 is going to be, well, my total is 50. And when we look at the, let me erase this. Look at my table here. From this given information, how many times was a 4 spun? Well, 14 times. So from this experiment, we're given the information that out of the 50 spins, 14 of those times it was a 4. So given this experiment, given this trial, we would say that the probability of spinning a 4 on my next spin is going to be 14 out of 50, or 7 out of 25, which could also write as 0.28. So that's the difference between theoretical and experimental. With the experimental, you're given data, and then from that data you count the probability of something occurring. Alright, So that is it for this lecture. If you guys have questions, make sure you shoot me an email. But yeah, have a good rest of the day.